Hi guys, in this video we'll look at synthesis of epoxides from alkenes, Roman numeral 3 here in our outline, and also synthesis of cyclopropanes, Roman numeral 4. Now these two reaction types are shown in our diagram here. Synthesis of an epoxide is shown here with a peroxy acid to give the epoxide. And then we have two different syntheses of cyclopropanes. Reaction with diazomethane to give a simple cyclopropane three-membered ring here where the alkene used to be, connecting these two carbons to one new carbon to make the three-membered ring. But we will also see a synthesis of geminal dichlorocyclopropanes, geminal meaning twins, two chlorines on the same carbon. Okay, let's begin by looking at synthesis of epoxides. Now epoxides is the three-membered ring, carbon-carbon-oxygen, three-membered ring. It also goes by the name of oxirane. That's actually the more official name, but most everyone calls them by a common name, epoxide. Epoxides are commonly made from alkenes by reaction with a peroxy acid. That can be condensed down to an R group CO3H, and a Lewis structure for that is analogous to a carboxylic acid, which would be carbonyl OH. But this has an extra oxygen between the carbon and the H. And oxygen-oxygen single bonds like this are called peroxides. And so this is known as a peroxy acid with the additional oxygen. We know we can abbreviate the carboxylic acid as RCO2H. But the peroxy acid is abbreviated RCO3H. Now, R groups can vary. Many different R groups, and it can still be a peroxy acid. The most common R group is a benzene ring with a chlorine in the meta position. And we'll learn ortho meta para in Organic 2. But meta is essentially a 1-3 relationship. If this is 1, the chlorine is at the 2-3. And so we can use the terminology metachloroperoxybenzoic acid. And MCPBA should be in just about any organic textbook as one of the most common peroxy acids. Okay, mechanism for this reaction. Well, previously we had looked at reaction with like elemental halogen, like chlorine. And we have to argue for an induced dipole, otherwise it's nonpolar, and an induced dipole leads to one chlorine being partial positive and the other being partial negative. And one of the chlorines is thus electrophilic, and the pi electrons of the alkene attack the electrophilic chlorine. Well, with the peroxy acid, it's very analogous. But which oxygen is electrophilic? And it's actually the end oxygen. Because we have dipoles on the right side. We have a carbonyl dipole, that oxygen pooling, And that's a significant pull because pi electrons here are very easily polarized. That's going to lead to pulling an extended inductive effect. And so these electrons are pulled. And then keep pulling. And then so we pull electrons away from this oxygen. And ultimately all the electrons move towards this oxygen, leaving this area over here partial positive. Analogous to this. And so the pi electrons question where we're going to make cation when our alkene reacts, left or right? Well, their answer, of course, is left. We'd make a tertiary carbocation. So these electrons swing away from that carbon, attack that oxygen, and we kick this oxygen off. Analogous to attacking this chlorine and kicking that chlorine off, the other chlorine off. This electron movement gives this intermediate here. This carbon is making a bond to oxygen. There it is. That's the bond we just made. That oxygen does have an H there. It doesn't magically disappear. There are two lone pairs here. But the other oxygen left this oxygen. And there it is. Because when it moves on, when these electrons move on to that oxygen, that's how we get the third lone pair. And that is a minus charge there. And here's our carbocation. But this is not actually formed because the new group has a lone pair. As we stated in a previous video, if the new group has a lone pair, it will immediately back bond. So these electrons come in here and back bond internally, intramolecularly. Okay? And that gives this structure when we just made this bond from the back bonding. And this is our first intermediate. This is not actually formed because the first two steps are concerted. As soon as the electrons attack the oxygen, these electrons are actually coming back over here at the same time. But I choose to show you this approach. I think it's the better way to try to teach you early on. Just make sure you understand that this is NAF. This is your first intermediate. This is very analogous to our halogenation mechanism to form a chloronium ion. All right, back bonding, boom, first intermediate. This is not actually formed. See the similarities, okay? Positive chlorine, positive oxygen. Now, a big difference is this oxygen can go neutral by something taking the H. And what can take the H? Well, the leaving group over here, which is actually sort of like an acetate or a carboxylate anion. These electrons, okay, these electrons make bond to H. This is a standard acid-base mechanism. These electrons move on to the oxygen to become the second lone pair. And we produce the oxygen now bonded to an H. That's what this arrow means. All right. And we produce two neutral products. And here's our peroxide. All right. As we said, very similar to a chloronium ion or bromonium ion, etc. The difference is this cannot go neutral by losing an H. And so something is going to come in here and attack this carbon, and the bromine gets one of the bonding pairs back to carbon. Where here the oxygen can get a bonding pair back from the H that was there. And the epoxide can actually indeed be isolated very readily. And you see ultimately that the peroxy acid has supplied an oxygen, and the end product is a carboxylic acid, where that extra oxygen is now gone. Now, an epoxide is a rather strained three-membered ring. That does not mean that we cannot make such a ring. They can be made. Now, they do tend to be fairly reactive. And we will learn about the reactivity of epoxides in Organic 2. Here in Organic 1, we see how to make them from alkenes. Again, see the consistencies in your mechanisms. By the way, I said that's the first intermediate. It's also the only intermediate, right? Then we get final product. Okay, in terms of just plain predicting a product, it's actually a very easy reaction to predict. Once we start considering stereochemistry of the addition, okay, it is an addition reaction, right? All of our reactions are additions. They're all electrophilic additions. Okay, we added an oxygen to this molecule. That's essentially what we did here. But ultimately, to simplify this down, the two carbons of the alkene become bonded to one oxygen. And if we show this down here, first off we assess, what do we have here? A peroxy acid. This is dichloromethane, okay? That's just a common solvent. And it's inert to most any of these reagents that we've been talking about. You need to be able to recognize a solvent. And in general, most of the time, a solvent will be unreactive. It's just there to dissolve the reactants. So the reactant, the key reagent or reactant here is the MCPBA. We know that's a common peroxy acid. And what does a peroxy acid do to an alkene? It converts it to an epoxide. And we can go boom, 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 boom. There's your carbon skeleton, and now these two carbons are connected to an oxygen, and we have two lone pairs. Standard bonding for oxygen, two bonds, two lone pairs. Now, this is a chiral carbon here, and just for our notes, this will be racemic. We can add that to our notes right now. So as we look back, once we cover more stereochemistry, we can understand that and think about that more. Okay, there's some below for you to try. Again, just connecting an oxygen to the two alkene carbons is pretty darn easy. That's just like when you do a halogenation, you're just connecting a halogen. Well, that's a halohydrin. You just connect a halogen, okay, to each alkene carbon. And you have two, and it's a dihalide. But the stereochemistry actually becomes a bit more involved. Okay? Now, let me see if I can sort of walk us through the stereochemistry of this example down here. With rings, stereochemistry is a bit more defined, and so it's actually a little bit easier to deal with a ring than the examples below. Now, if we don't consider stereochemistry, again, this is simply, there's your backbone, and the alkene carbons are now bonded to an oxygen. And there's your product. But what about stereochemistry? Because if we look at this, the two carbons of the alkene are now tetrahedral, and ultimately with rings, the groups can either be cis or trans. Well, the answer is for example, this top carbon, 2 in the plane, let's consider the 2 bonds in the ring in the plane, then let's put 1 forward, let's put the methyl forward, well then the oxygen is going to have to be back. And there's a tetrahedral carbon. But the carbon below is also tetrahedral. 1 forward, 1 back. The bond to the oxygen is going to have to be back. And then the undrawn H would be forward here. Now, we'll go through why. Ultimately, the oxygen is going to be sort of cis, or a syn addition, same side. But we'll also get the enantiomer. And often we can show like this. Racemic. That's what racemic means. Okay. What will the enantiomer look like? Again, we've mentioned this before. That's where all of your stereochemistry is switched. And so the methyl is back. The oxygen is forward there, but also forward here. And that's the enantiomer. You will not get any product where the 2 bonds to the oxygen are trans. 2 reasons. First off, it's just impossible. Because if one was one way and the other bond was the other, this bond could not be bonded to that oxygen. Both bonds have to be the same way. You just cannot have a trans 3-membered ring. Okay? But we can also look at it mechanistically. All right. When this attacks and these electrons come in here and attack that terminal oxygen and kick this one off, okay, that's going to give our intermediate, okay, if we show a carbocation, which is not actually formed, that's trigonal planar up there still, sp2 trigonal planar, but the bottom carbon is now tetrahedral, and it's either going to be forward or back. I can draw this back. Okay. Plus the essentially the leaving group. But look at this here. Now this back bonds here. But if this bond is back, and then the oxygen bonds to the carbon, that bond has to be back as well. Okay? It just has to be. It's coming from the back. If a bond is coming from the back, it's like if you throw a dart at a dartboard. If you're over here and you throw a dart at the dartboard, the dart is going to be stuck in the dartboard, but it'll be projected back because it came from the back. Unless you throw a boomerang and it goes around to the other side of the wall, it comes in this way. If you ever throw a dart like that, please let me know. I'd like to see that curveball. If the OH is back, the new bond has to be back. Alright, and then you lose the H, and so I'm just going to show kind of multiple arrows. I'm not really showing full mechanism. Alright, but this could also be forward, and if the oxygen is forward and when it back bonds, the new bond would also be forward. So that's how you get to enantiomers after you lose the H. So ultimately, we need to be able to consider the stereochemistry of these addition reactions when we have stereochemistry. Now down here, the stereochemistry is a little touch more difficult. I want you to work on these, and then we'll look at them probably in class. The difference is these two alkenes here are both stereogenic, and that kind of gives me a clue that the stereochemistry of the product is going to be a touch more complicated than above, because the above alkene was not stereogenic. Okay, I'm going to wait to cover these. Give you a chance to think about those. Again, just predicting the product with no stereochemistry, you just hook an oxygen to the two alkene carbons. And that's your epoxide. But we need to also be able to consider the stereochemistry. And we'll keep working towards that. Okay, on our outline, did we cover everything about epoxides? It is a cis addition. Yes. Yes. Okay, the two bonds, it's a syn addition of the oxygen. But this is not something we just memorize. We see that through the mechanism, okay? And stating that it's a syn addition is just a statement after the fact. Syn and cis are almost synonyms. Cis is more of the stereochemistry of the final product. Syn is more of the mechanism. And your mechanism is always syn, but your product is not necessarily always going to be cis. That doesn't mean it's going to be trans, but sometimes cis just may not be applicable. But the mechanism is always a syn addition of the oxygen, because when it back bonds, all right, anytime you back bond, it's going to be syn. because the new bond, the projection of the new bond is based on the projection of the existing bond here. Okay. Yes, it's concerted. The first two steps are concerted. That's why the intermediate is not actually formed. Well, careful, it's not an intermediate. That's why my first fake intermediate, my first structure, is not actually formed, because the first two steps are actually concerted. And we talked about how it's similar to making a bromonium or chloronium ion, but epoxides are certainly can be isolated much more routinely. Okay. The next reaction here is going to be synthesis of cyclopropanes. And we're going to see that this is by addition of carbenes. Okay? All right. Two different carbenes we'll look at. The simple CH2 carbene, which comes from diazomethane. And this is diazomethane. It's one carbon and it's got two nitrogens there. That's where that name comes from. And we get a cyclopropane. So the two carbons of the alkene, original alkene, are each become bonded to one carbon, not an oxygen, but one carbon. And now this is a three-membered hydrocarbon or carbocyclic ring, all carbons. And of course that's a cyclopropane. And this is a common way to make cyclopropanes. Mechanism. Now diazomethane, we can show a Lewis structure like this. It's going to be dipolar. It's net neutral, but the carbon is going to have a minus and the nitrogen is going to have a plus. We could show other Lewis structures, other so-called resonance structures, but this one here is sort of the most relevant and most useful when doing the mechanism here. And with heat, okay, this universal symbol for heat, delta, this nitrogen will just leave. Okay, it would love to have electrons. It's positively charged. If it just takes them and leaves, if it just ionizes, gotta be careful, it's already ionic. And this is sort of just leaving group leaving. That leads to, first off, if that just leaves, we get nitrogen gas. Okay, up arrow indicating gas, N2, this is a Lewis structure. And so when it leaves, the nitrogen gets back the lone pair, and it becomes a very stable N2 molecule. No longer positive charge. Well, the carbon, okay, now, well, why does it have two charges? Well, let's look at this closer. We got a carbon with two H's bonded to that. Okay, there is a lone pair here. That's a plus, and this is a minus. Net neutral molecule, just like what we showed here. When this leaves, that gives the nitrogen, but then we have a carbon with two H's and a lone pair. And that's it. And if you look at the charge here, the charge of this carbon is, well, it owns 1, 2, 3, it owns 4 electrons. And that's how many it's supposed to own. So this carbon is actually neutral. And this is an exception to lecture 1, basically. We said standard bonding for carbon is 4 bonds, no lone pairs. And we said if it wasn't standard, it's likely going to have a charge. Well, this is a case where it's not standard, but it also does not have a charge. It's neutral. It is called a carbene. Okay? It's divalent. That means it has two bonds. Carbenes are divalent. All right? They always going to have one lone pair. And they're going to be neutral. Now, importantly, they don't have an octet. And thus they are electron deficient. And if we graph the hybridization of a carbene, all right, let's take time to understand structure here. Three electron regions around the carbon, all right. So we expect it to be sp2. sp2 is going to be three hybrids and one p orbital left over, all right. And the three regions are a bond to H, and a lone pair. And the four arrows are the four valence electrons of the carbon. You see it's neutral. And we have an empty p orbital. No octet. It only has 2, 4, 6 electrons. All right. This carbon would actually like to get, even though it's neutral, all right, it would still like to get electrons to fill its outer valence shell. So this is electrophilic, even though it's neutral. It likes electrons even though it's neutral because it has an empty p orbital, because it doesn't have a filled outer shell, a filled octet. All right. Now we can finish this up. We expect trigonal planar, and thus this carbon has H, H, and this region is a lone pair. And so this bond angle here would be 120. It looks 90 as I drew it. It's a little wider because I didn't quite draw it 120. So all this is fundamental structure. Now, why do I show two charges? That's because it has sort of dual character. Usually when carbon has a lone pair, usually it's a minus, and that lone pair will kind of act as a nucleophile. Okay? It's got a lone pair. Tends to be a nucleophile. Things with lone pairs can act as nucleophiles. But it's also electrophilic. All right? It's net neutral. The plus and the minus is often shown to sort of reinforce the dual character of the carbene. All right. We can show it without the two charges. We can just show it condensed. Pi electrons attack. Why would it want to attack? Well, you see, we really need to know all the structure here, and I went through that. The pi electrons attack. Where are we going to leave carbocation, left or right? Well, it would be left, and so these electrons attack the carbon. What are they attacking? They're really filling that empty p orbital. Okay, electrons are moving into this. All right, and that's going to give, well, I'm showing it here. All right, it's It's going to give bond, that's new bond to the carbon, but there's a lone pair there. Now it's actually a minus charge. And sort of the carbocation nature is now gone. This thing is minus. Here's the carbocation. And the new group has a lone pair, and anytime the new group has a lone pair, these electrons, it will back bond. And when it back bonds, what do you get? Well, you get product. That's it. Carbon with two H's. And this is not actually formed. And thus, this reaction has no intermediate. That is, the alkene attacks the carbon, and at the same time, the carbon lone pair is back bonding in one transition state, and bam, there's your there's your cyclopropane. Now, there's no intermediate in the mechanism of the alkene reacting with the carbene. Okay. Now, in practice, diazomethane is a little bit hard to handle. It's a gas. Okay. So you're not going to be able to just weigh it out. It's also explosive because it's a little unstable. It's ready to just decompose. A little bit of heat, or even potentially some pressure, or some type of energy input, and we can get enough energy to meet the transition state for this nitrogen to just leave. And when one molecule becomes two, that's going to build up pressure, and that's going to lead to an explosion, depending on how much you have. So you've got to be very careful using diazomethane. It also tends to be toxic because the carbene is fairly electrophilic. And electrophilic species tend to be toxic because if they get in the body, the nucleophiles in your body will start reacting with them. That takes us to another carbene, the dichlorocarbene. And here it is here. Instead of two H's, it has two chlorines. And it comes from chloroform. And while chloroform is slightly toxic, it's not so toxic that it's going to be prohibitive and dangerous as long as we take normal precautions. And so making dichlorocarbenes is much easier. And this will give a cyclopropane with two chlorines on the new carbon. Now, of course, you're going to be stuck with two chlorines there. But it is an easier and thus a fairly common reaction. Okay, mechanism for this. Here's your chloroform. The H of chloroform is slightly acidic, and hydroxide, which is included, such as sodium or potassium or lithium hydroxide, etc., will actually act as a base and take this H, standard acid-base reaction, and we can get a carbon with a lone pair, plus water here. Now the carbon with a lone pair is analogous to the diazomethane structure, and then the nitrogen left because it wanted its electrons back. Well, the same thing happens here, except one of the chlorines leaves. Not because it's a positive charge, but because chlorine tends to be greedy and it likes to become minus. And so that leaves, and that generates your dichlorocarbene. All right? Again, you don't have to show the two charges, but it's now neutral. And another reason for this chlorine to leave is chlorine sort of tells, if they talk to each other, chlorine's like, well, I'll leave and I'll become minus, And you can go back to neutral carbon. So I'm taking on the electron density. I'm more greedy anyway, so I'm happier like this. Also, one molecule is becoming two. Of course, that's not a molecule. But one species is becoming two, and so this is also driven by entropy. So chloroform in the presence of hydroxide will form the dichlorocarbene fairly readily. Then if the alkene is around, it'll attack. All right, and make the bond to the carbon. Lone pair there. It will immediately back bond. I say immediately, it's actually back bonding at the same time. And this is not actually formed. And so, bam, this forms the dichlorocyclopropane, and there's no intermediate. So this is just sort of, to me, always been a fascinating reaction. We can get fairly simple reactants here to generate this reactive intermediate, and the alkene reacts with it to give a gem dichlorocyclopropane. Okay, so here's a couple below with diazomethane and also chloroform and hydroxide. Anytime you see chloroform and hydroxide, it's going to be looking to form the dichlorocarbene. Did we cover everything on our outline? Concerted? Yeah, it's concerted. It's just like making bromonium ion, making epoxide. See the similarities in your mechanism, a three-membered ring, except this time the new group is carbon. Drug topic. Is that handout here? Maybe it's here. Okay. I give you a handout here. Cyclopropanes are actually, even though they're a strained three-membered ring, they're actually fairly common, particularly in drugs. A number of drugs contain the cyclopropane ring, and here's some examples. Okay. Including Cipro, which I've shown before. Okay. This drug here, the cyclopropane, is fused to a five-membered ring. There's also a cyclobutane in this molecule. This one here, we have stereochemistry on the ring. I turn it like this. Okay. The benzene ring, the phenyl, and then this methyl amino group are trans to each other. Remember, on rings where their stereochemistry is fixed, groups can be cis or trans. And so this amide group and the methyl amino group are cis on the ring. And then I think over here is where I mentioned on the outline where a carbene is actually formed in the metabolism of this drug. And so understanding the structure of carbenes, we can then read and understand this metabolism here. And it's divalent, so both H's are removed when the carbene is formed. I don't know what mechanism that is. Okay, we can see if it discusses a mechanism. But I think the drug company would like this to not happen, And I think what they're doing is they were looking to replace the H's with deuteriums, which is an isotope of hydrogen. And probably because if these are deuteriums, formation of the carbene is going to be more difficult. And so that would be a way to stop this from happening in vivo or in the body. But you can read about it. It's an interesting application of carbenes to drug metabolism. And in test 3, we will look at the kinetic isotope effect, the difference between bond strengths between a H and a D, and how that can lead to different kinetics for reactions. Okay. The next video we'll be looking at the next 3 topics: oxymercuration, hydroboration, and hydrogenation of alkenes. And those are shown on the outline. We'll be finishing up these 2 here. And both of these reactions give alcohols. They're specialized ways to make alcohols, where up here this is more of a generic way with the acidic water. And then we'll be looking at this reaction down here, catalytic hydrogenation of alkenes using hydrogen. Okay guys, that ends this video here.